Hi everyone, my name is Quỳnh Anh. Today I would like to talk about my study with the title Tunability of Magnetism in Heusler Mn3Ga crossover between cubic and tetragonal phase upon cobalt substitution. First, let me introduce briefly about Heusler compounds. Let me start with a rock salt structure and then adding red atoms, it becomes Heusler structure. Periodic table contains elements with different color, according to color of atoms, here red, blue, and green, and then if you mix them together, you can design new Heusler compound. Do you know by that way first Heusler compound was synthesized by Fritz Heusler? He mixed copper, manganese, and aluminum together. It behaves ferromagnet. Up to now, Heusler compounds contain the huge number of members, and they become potential candidates for magnetic and spintonic devices. Because of their multifunctional property here, including metal, half metal, semiconductor, exhibiting ferromagnet, and so on. Especially magnetic moment of cubic Heusler compound can be predicted by Slater-Bowling rule. This formula, where MT is total magnetic moment and ZT is valence electrons. Here, this figure, you can see Slater-Bowling rule works well for a lot of Heusler compounds. But I just provide two examples. First compound ZT24, MT0, and it is semiconductor. Second compound ZT is 30, so MT is equal 6. With more valence electrons, minority spin is shifted down, so it becomes half metallic city. Now, if we doping or changing components, we can change valence electrons. So we tune magnetic moment and find half metallic city. Among them, manganese-based Heusler compound attract great attention because of their multiple structural phases with different magnetic configuration, leading to novel properties to compare to other Heusler compounds. For example, spin orbit torque applications, anomalous Hall effect, or even compensated ferrimagnet. In my case, I concentrate on Mn3Ga. It has three different phases: cubic, tetragonal, and hexagonal phase, and the most stable phase is tetragonal. Here cubic structure, and then with 001 distortion we can get tetragonal structure. Manganese locates at two different equivalent sites, manganese 1 octahedral and manganese 2 tetrahedral. They exhibit antiferromagnetic ordering but not cancel each other, so it is ferrimagnetic. Tetragonal distortion leads to high PMA, moreover it has high TC and high spin polarization, which are good for spin transfer torque applications. Nowadays there are some experimental papers that use cobalt to substitute into manganese 2 side to tune magnetic moment. Here we can see structural transition occurs. For tetragonal phase, magnetic moment decrease, and then it increase and follows Slater-Bowling rule for cubic phase. So we want to know why it happened. That's why I choose cobalt to substitute to Mn3Ga. This is my calculation method. I use VAPSUP to run DFT calculations. Here's some calculation parameter. Otherwise, I use opponent map to find exchange interaction. Now this is my result. First, I substitute cobalt into both manganese sites. The figure shows energy difference between them. It indicates that cobalt prefers manganese 2 side. So later on, I just concentrate on manganese 2 substitution only. The figures show energy difference between tetragonal and cubic phase depending on cobalt concentration and C/A. There are two red dots right here. The first one for cubic phase, C/A around 1.4, and the other one for tetragonal phase. With the cobalt, black line, tetragonal phase is more stable. Blue line is also, but red line x equal 1, cubic phase become more stable. So increasing x, structure changes gradually from tetragonal to cubic phase. That's why I provide second figures with more cobalt concentration. And I found that structure transition occurs around from 0.5 to 0.67. Now we look at total magnetic moment. You can see that cobalt into different phases show different magnetic behaviors. The total magnetic moment decrease for tetragonal phase and then is increase for cubic phase. These results are consistent with experimental results which I saw before. To explain magnetic tendency, I provide the atomic magnetic moment. You can see the value of manganese 1 and manganese 2 moment not change much in both tetragonal and cubic phase. Even change the spin direction. Now I want to remind you I substitute cobalt into manganese 2 side. For tetragonal phase, cobalt moment is extremely small. So, increasing cobalt concentration like removing manganese 2 atoms out of system. That's why total magnetic moment decrease. Now for cubic phase, cobalt moment is around 1 magneton more. So increasing cobalt concentration like increasing positive content and reducing negative content of manganese 2 atoms. Eventually, total magnetic moment increase. Well, now we have cobalt moment in tetragonal phase is also strange. And I want to explain why it happened. That's why I provide density of state for cubic and tetragonal phase at x equals 0.5. First, we look at total density of state. Gray field area. We can see cubic phase is half metallicity, with spin polarization at Fermi level almost 100%. Now from partial dot, we can get more information relating to magnetic configuration. And to have it easy to visualize, I plot the dot diagram. And I start with the tetragonal phase. Manganese 1 blue one with larger exchange splitting, so it has larger moment. Manganese 2 red one with smaller exchange splitting and it has smaller moment. Cobalt is substituted in manganese 2 side, so it looks similar to manganese 2. But the minority spin is shipped down because it has more 2 electrons than manganese. So cobalt with negligible exchange splitting, so it has extremely small moment. Now for cubic phase, you can see manganese 1 and manganese 2 exhibit similar behaviors, but cobalt with bigger exchange splitting, so it has bigger moment than that in tetragonal phase. To study magnetism and related phenomena, we also provide exchange interaction, where Heisenberg model is employed as a convention. Here Zij is exchange interaction, and at I and at J is spin direction. Negative Zij is antiferromagnetic ordering, and positive Zij is ferromagnetic ordering. By that way, I get my result. You can see manganese 1 and manganese 2 give antiferromagnetic ordering in red bar. Cobalt manganese 1 and cobalt manganese 2 show opposite behavior in different phases. And these results are consistent with magnetic configuration which I talked before. Especially, cobalt manganese 1 coupling in cubic phase is 5 times larger than that in tetragonal phase. The last is my conclusion. First, we found that structural transition occurs around from 0.5 to 0.67. The second, cobalt magnetic moment in 2 phases are different, especially the extremely small moment for tetragonal phase. And finally, exchange coupling between cobalt manganese 1 and cobalt manganese 2 show opposite behavior in different phases. And that's all, so thank you for your attention.